Hello Math 1316 students, let's begin lesson 2, trigonometry of acute angles, or equivalently, the trigonometry of right triangles. Any acute angle can be inscribed into appropriate right triangles, so they mean the same thing. Let's begin with a bit of a review, however. Last time we studied radian angle, remember that? The relation between the radian measure and the arc length, like this. Remember that? Radian measure is measured from an arc length starting from the x-axis to the right, counterclockwise, and then divide by the radius, because the longer the radius, actually the arc length will be proportional to the radius. Everything is one-dimensional, so radius is extended by factor of 3, and then of course arc length will be extended factor of 3. Area will of course extended factor of 9, 3 squared. You have those kind of dimensional relations really, but I want dimensionless quantity that stays the same. That's the angle. So we want S over R, that ratio that stays as constant. And that's how we are going to get S equals R theta. I didn't tell you about the dimension argument in the previous lesson, so I wanted to talk about it. A bit advanced here, I know, but hey, we already went through lesson 1, so we are in a little bit more advanced stage. Clockwise, positive direction. Counterclockwise. No, I said it backward. Counterclockwise, positive direction. Clockwise, negative direction. Yeah, went through that too. And then the convergent factor of 2 pi over 360, or equivalently pi over 180. We went through that too. 360 degrees for full rotation, which is equivalent to 2 pi for entire revolution, entire full circumference. And then arc length formula and area formula. I saw some students getting confused here with these. Let me tell you briefly again, because I was compelled by students to review this. These work for radian measure, and of course relation between S and R came directly from the definition of the radian measure or the dimension argument. But if you don't like it very much, then there's an alternative argument. Let's begin with entire circumference 2 pi r, and then let's consider the portion of your arc only. And your pi is not the entire pi, but only theta radian out of total 2 pi radian. So that's the ratio you have to multiply. Theta over 2 pi and simplify. Same argument applies for area formula as well. The entire area inside of the circle, pi r squared, and then we don't own the entire circle. We own only a slice of pi. So we have to multiply that ratio, theta radian out of total 2 pi radian, multiply that and simplify so that we get this formula here, 1/2 r squared theta. And they're both depending upon this ratio is a radian measure, theta radian over 2 pi radian total. If you use degree measure, then degree over 360 degree total, degree measure over 360 degree total. So conversion is a little bit different. Okay, that's the question I got. So, alright. There goes a brief review, and now let's go to section 1, and let's begin discussing the trig ratios. In high school geometry, how did you define sine, cosine, and tangent there? Opposite of hypotenuse, adjacent of hypotenuse, and opposite of adjacent. And cosecant, secant, and cotangent were their reciprocals. One over sine, one over cosine, one over tangent, respectively. Remember that? You can draw the picture like this. Yeah, for example, let's suppose we have a right triangle like this, and then here's my angle in question. Theta. And then this is my right angle. And then of course this is the hypotenuse, opposite of the right angle. And then this is the adjacent to this angle theta. And this one is the opposite of the angle. So sine of theta is the opposite of hypotenuse, O over H. Cosine of theta, adjacent of hypotenuse, A over H. Tangent of theta, opposite of adjacent, O over A. And we can get cosecant, secant, and cotangents by the reciprocals. One over sine, one over cosine, and one over tangent. And the beauty of this argument here is that it works for arbitrary right triangle no matter how it is positioned. It always works whenever you have a right triangle. That certainly is an advantage. In a college level course, however, we're going to take a bit of a detour. Instead of that direct method, which applies to any right triangle no matter how it is positioned, let's take a detour toward a circle, and let's inscribe the right triangle to a circle in a strategic fashion, and then go from there. Why am I taking this detour? Because this detour allows us to expand our argument beyond the acute angle, going to obtuse or arbitrary angles, negative angles, and so on and so forth. How do we do that? Angle in question always go to the origin. Remember, observer is sitting at the origin, and that observer is measuring the angle. So angle in question must go to the origin. And then the right angle goes to the x-axis. And that's how you get this horizontal squared, vertical squared is hypotenuse squared, rewritten as x squared plus y squared equals r squared. The radius is the hypotenuse in this case. One of the common mistakes here is to do this. Drawing your triangle where the right angle is at the origin. And this will earn you automatic 0 credit because you cannot do anything here. Angle in question may be this or that, but the observer is sitting at the origin. The observer cannot measure the angle. Nothing works from here. Automatic 0 credit. Another convention students sometimes use is to draw the right angle at the y-axis instead of x-axis. This is not automatic 0, but it's confusing and it requires some extra step. And if you don't take that extra step, things can go wrong. So you may earn some deduction here like this. It's not automatic 0. It's better than getting the right angle at the origin, but still not very good. Don't do this. So the key point, the angle in question goes to the origin, and the right angle goes to the x-axis. Once you do that, based upon that picture, we can redefine sine, cosine, and tangent like this. Vertical over radius, horizontal over radius, and vertical over horizontal. Is it better? Yes, it is. It'll turn out to be better. Yes, if you stick to opposite of hypotenuse, adjacent of hypotenuse, opposite of adjacent, it'll continue to work out okay, because after all, you're sitting right here. That's the observer, and the angle in question is here, and vertical is the opposite, horizontal is the adjacent, and radius is the hypotenuse, so it'll work out okay. But the reason I'm emphasizing vertical, horizontal is because in coordinate axis, horizontal is x, vertical is y, and then x and y values can be negative if you go to second, third, and fourth quadrants, you see. You can go further. And that's why I'm emphasizing the new convention here. And I'll try to follow these, even though opposite, adjacent, hypotenuse, that convention will work for this lesson, lesson 2, for acute angles. In order to go further to obtuse angles, I'll try to use these terms. Okay, ready for an example problem? Okay, all right. I guess so. Cosine of alpha is 3/4, and it's an acute angle, yeah, greater than 0, less than pi over 2. In other words, greater than 0 degrees, less than 90 degrees. Find the other trig values of alpha. Well, all right. Cosine of alpha is 3/4. And what is that? It's x over r, horizontal over radius. From that, you can easily deduce. You can put x is 3, and then r as 4. And the question now is, what is y? If you find y as well, then you get y over r sine, y over x tangent, and then take the reciprocals, 1 over sine, 1 over cosine, and 1 over tangent. You're going to get all 6 trig ratios. So this is a key point. What is y? Can you figure it out from this right triangle? Stop the playback and do that. Did you get it? Well, I redrew the picture here, and then use Pythagorean rule here. 3 squared plus y squared is 4 squared, the hypotenuse squared. So y squared is 16 minus 9, so y is square root of 7. Alright, I have y value. So using definitions of sine, cosine of tangent, and then their reciprocals, we get all 6 quantities like this. I have many problems like this in Pearson My Math Lab, and also in handwritten exercise set as well. So go ahead and review those. Now, enough time for another problem here. Not enough time, so let's stop here, and we'll revisit this problem in the next video. Remember, when you place a right triangle to coordinate axis, the angle in question goes to the origin, and the right angle goes to the x-axis. Remember that, and you'll succeed.